Here's a couple pictures of some people floating in the Red Sea. I've never been, but I've heard that the popular thing to do is float on your back, and if you want to make it a good photo opportunity, you bring some reading material with you. And the reason you can float so easily is because the very high salinity of the Red Sea makes the water quite dense, and so its density is enough that it supports our bodies. Our body overall is less dense than the seawater in the Red Sea. This has to do with Archimedes' principle, and Archimedes' principle is stated just below these two pictures. It says that the upward force that acts on any object, whether that object is partially submerged or completely submerged, there's a couple people that are only partially submerged. Anyway, that upward force is exactly equal to the weight of the fluid that's displaced by whatever the submerged object is. So if this person was not floating here in the water, what would take up the space that she's occupying? Well, it would just be filled in with water. And same with this guy. He's displacing some water. If he were taken away, water would come and occupy the space that he's currently in. So the weight of the fluid that would fill that space back in is what we call the buoyant force on the object. Okay, so what do you think about this? True or false? Here we have a picture of a floating boat. True or false? The reason the boat floats is because it weighs less than the buoyant force. In other words, the buoyant force is even greater than the weight of the boat. I hope you said false. Let's picture a free body diagram. Let's say that vector represents the weight of the boat. So if the buoyant force was greater than the weight of the boat, it wouldn't be in equilibrium and it would accelerate upward. If the buoyant force were less than the weight of the boat, then the boat would be sinking. So what's the situation when an object floats? Yeah, if the object floats, then the buoyant force and the weight are equal to one another. So notice the Archimedes principle doesn't mention the word floating anywhere in it. That's because Archimedes' principle is not a rule that decides whether or not something floats. Archimedes' principle is just a principle that tells us how we can calculate the buoyant force. Here's how we calculate it. The buoyant force is equal to what? The weight of the fluid displaced. So the buoyant force is equal to, let's see, if I multiply the mass of the fluid times gravity, that would be the weight of the fluid displaced. Now, by the way, the mass of the fluid is the density of the fluid multiplied by the volume of the fluid. And we can picture the fluid displaced like this. That volume that's currently being occupied by the boat, when the boat leaves, would be filled back in with water. And the weight of that water is equal to this buoyant force. So let's say that just one more time. Archimedes' principle can be stated mathematically as an equation. The buoyant force on an object is equal to the density of the fluid that it's submerged in times the volume of the fluid displaced by the object times gravitational field strength. Maybe we should get into a description of exactly where that equation comes from. So let's picture an object that's completely submerged instead of this boat, which is partially submerged. And by the way, Archimedes' principle applies to both cases. Whether something is partially or completely submerged, the buoyant force can be calculated in this way. But let's focus for now on something that's totally submerged. So let's say we have a cube. We'll just draw it two-dimensionally here. And the cube has a top surface that sits at a depth, how about we call this y number 1, and the bottom surface sits at a depth we can call y number 2. Well, maybe we'll draw it three-dimensional. Okay, so our cube has a surface area of A, and we'll say it has a height of h. And by the way, you can see that h would just be equal to y2 minus y1. So remember that pressure varies with depth. Gauge pressure is density times acceleration due to gravity times depth. Here I'll say y instead of h, since I'm referred to h as the height of our object, and I'm using y as a depth measurement. Okay. Absolute pressure is equal to atmospheric pressure plus gauge pressure. So what's the pressure at the bottom? The pressure at the bottom is atmospheric pressure. Now, keep in mind what atmospheric pressure is all about. That's due to the weight of all of the air above sea level, okay, plus some gauge pressure. Well, the gauge pressure at the bottom surface is rho times g times y number 2. So that has to do with all the fluid from the surface to the bottom pushing down. Then there's a pressure acting at the top. And the pressure at the top, in the same way, is atmospheric pressure plus rho times g times y1. So that means there's a couple of forces. There's a force pushing down from the top, and there's a force pushing up from the bottom. These forces aren't equal. Force is pressure multiplied by area. Well, the area of the bottom surface is the same as the area of the top surface, but the pressure at the bottom is greater than the pressure at the top because y number 2 is deeper than y number 1. So the net amount of force should be equal to the force at the bottom minus the force acting at the top, and that's an overall net force that pushes upward on this block. So let's see what we have here. Let me clear some space. That means the net force is equal to force at the bottom minus force at the top. Okay, well, force at the bottom is atmospheric pressure plus rho times g times y number 2. Then I have to subtract from that the pressure at the top, so minus atmospheric pressure plus rho times g times y number 1. So when I combine those together, I get rho g times y2 minus y1. Now wait a minute, I haven't found the net force here, I've found the net pressure right here. To get net force, I have to multiply the net pressure times the area. So we get rho g y2 minus y1 times area. But as we said earlier, y2 minus y1 is just the height of this object. So we get the net force is equal to rho times g times h times a. But you recognize what h times a is. If we multiply the height of this block times the area of its top section, that's just its volume. So we found that this net force is rho times g times volume, or we could reassociate this as rho times v times g. But rho times v, if this is the density of the fluid, right? In all these cases, gauge pressure is due to the density of the fluid. So here we have the density of the fluid. The volume is really the volume of this block, but the block is displacing, since it's fully submerged, the block is displacing a volume of fluid equal to its own volume. So although you might be thinking of h times a as the volume of the block, it's also the volume of the fluid displaced. So if I multiply the density of the fluid displaced times the volume of the fluid displaced, that's the mass of the fluid displaced. And mass of fluid displaced times gravity is the weight of the fluid displaced, which brings us back to the statement of Archimedes' principle that says the upward force is equal to the weight of the fluid displaced. We call that buoyant force. So there we have it. You can always calculate buoyant force by simply multiplying a density times a volume times g. Keep in mind, this is not the density of the object that's floating. This is the density of the fluid it's floating in, and the volume here is the volume of fluid that's being displaced. Important equation. Back to a floating boat. What if there was a bowling ball sitting in the boat, and then you dump the bowling ball overboard? Splash. What happens to the boat? Well, yeah, it's going to sit a little bit higher in the water now, isn't it? The boat will come up. The question is, how much higher will the boat sit in the water? Well, enough that the difference in the volume of water displaced is equal, has that volume of water displaced difference would have a weight equal to the weight of the bowling ball itself. Okay. Maybe this is a better question to test your understanding of Archimedes' principle. Here's 4 blocks, A, B, C, and D. A styrofoam block, a wood block, a plastic block, and a lead block, right? Styrofoam, wood, plastic, lead. The one thing they have in common is they're all the exact same size. Let's imagine they're all cubes with the same dimension along their edge. Can you rank these in terms of their buoyant force from greatest to least? Which block experiences the greatest buoyant force and which block experiences the least buoyant force? I'll give you a minute. Think about it, and on your own paper, scribble down an answer. Rank these blocks in terms of the buoyant force they experience from greatest to least. I'll give you 2 possible answers. A has the greatest, B has the second greatest, C has second to last, and D has the least buoyant force of all. Or, here's another option. The buoyant force on D equals the buoyant force on C. The next greatest buoyant force would be B, and the least buoyant force of all would be A. Which answer did you come up with? Those who say it's answer number 1 might think of it like this. Well, the styrofoam is floating the most, so to float the highest, it must be feeling the greatest buoyant force. And then the wood doesn't float quite as high, but at least it floats above the water, so it must have the second most buoyant force, and on the logic goes. If you thought that way, you're not taking Archimedes' principle at its word. The buoyant force is equal to the weight of the fluid displaced. Which one of these blocks displaces the most amount of fluid? Well, both C and D displace the same amount of fluid. They displace a volume of fluid equal to their own full volume. So this is why D and C rank equally as the 2 objects with the greatest amount of buoyant force acting on them. Then comes B, it displaces this much volume. And then lastly, A, which only displaces that much volume of fluid. Let's draw some free body diagrams to help you understand why 2 is the correct answer. For all of the blocks, there's one force that I can draw the same, okay? We can say a force of mg pulls down on every block. Oh, no, those aren't all the same. They all point in the same direction, but those aren't all equivalent forces. Lead is more dense than plastic, so the heaviest object of all has the largest mg vector. Then the plastic has a mg vector that's not quite as long. The wood has a vector mg that's still a little bit shorter. And finally, the styrofoam has a vector mg that's shortest of all. Well, if each one that's floating has a what we call neutral buoyancy, then the buoyant force would look like this. I know because it's in equilibrium, the buoyant force acting on the wood block is a vector that's just as long as its weight vector. And if the styrofoam is floating, its buoyant force vector is just as big as its weight vector. If the plastic is floating, its buoyant force vector is just as big as its weight vector. Well, here's one exception to that rule. The buoyant force vector on the lead has to be as great as the buoyant force vector on the plastic because they both displace the same amount of fluid. So if I draw an upward vector that's only as long as the buoyant force on object C, then it's not big enough to account for the downward force. So what's missing here? Yeah, you've probably figured it out. There's another vector, isn't there? In the case of the object that rests on the seafloor, it makes contact, and so there's an additional normal force that adds with the buoyant force. So we could say something to the effect that in case D, the buoyant force plus the normal force is equal to mg. But in all the other cases, A, B, and C, the buoyant force is equal to mg. So if we just answer the question based on the size of the buoyant force vectors we've drawn, D and C have equal buoyant force vectors, B has the next largest, and A has the smallest buoyant force vector of all. Okay, one last question about putting this idea of Archimedes' principle, form a challenge question out of this, test your understanding. Let's go back to that idea of taking a bowling ball, and putting it in a boat. But this time the boat isn't in the open ocean, it's in a contained, maybe like a large swimming pool or some sort of tank of water. And when the bowling ball rests in the bottom of the boat, then the water level where it meets the edge of the pool is clearly marked. So let's say when the bowling ball was in there, we use some paint or something like this and we mark where the water meets the edge of the pool. That was when the bowling ball was inside. Now we take the bowling ball and we set it out on the pool deck. Now you know what's going to happen to the water level compared to the marks. Yeah, of course, the water level is going to drop a little bit, right? Because it no longer has to support the weight of the bowling ball. But that's not the question I want to present to you. I want to ask, what happens when I take the bowling ball, throw it overboard, splash, and it sinks and now sits at the bottom of the pool? Now what happens to the water level in the pool? Does the water level increase and now meet the pool here? Or, I'm sorry, does the water level decrease and now meet the edge of the pool here? Or will the water level increase? Write your answer down somewhere. Let me ask another question. What if it wasn't a bowling ball? What if I had a piece of styrofoam that was sitting in the bottom of the sailboat? And then when I throw it overboard, it goes, well, sort of splash, and then it comes to rest right here. Now what happens to the place where the water level meets the pool? Oh, and I didn't give you a third option here. It's option A, it rises, B, stays the same, or C, it falls. And then I'll ask the same question about the styrofoam. Water level rise, water level stay the same, water level fall. Okay, well, I'll just leave you to think about the answers to those questions. Maybe we'll answer them in the next video segment.